Okay, so you can see I've uploaded all the content that is required for the course. So these are lecture 0 PPT, lecture 0B, lecture 0C. These are the original PPTs. We are updating like as because for every instructor is using this PPT. This is the base PPT. And then they are adding examples. So I've also added examples, and that PPT I'll upload in the Teams. And these are the quiz one that is ungraded. So it's just for your practice. Then this is the practice assignment. This is the reference for linear algebra. You can have it online. Okay, this book you can practice some questions. It's just for your reference for only for zero course. And then this is the reference for calculus, Thomas calculus. So I hope this web page is visible to all. Like you can access it. All right, let's get started now. Okay, so let me share my PPT.
A quick question. So there will be 4 classes, right? So there are 3 PPTs. So does this cover all four classes, or there
Yeah,
will be
all
one
the
more?
four.
Okay, sure. Thanks.
Okay, so we were here. Lastly, we were discussing, this REF. So REF is very, very important concept because it is used everywhere. Whether you want to solve determinant, whether you want to find the inverse. So we'll do one practice problem. Can you see the slides in full? Full slide is like, I hope you can see. Is it fine? Or it's not full slide? Just
No, I think you have
please
to
check.
swap.
Swap.
Yes.
Is it okay now? Okay. So last time we talked about just basics. Okay, like what is matrix? Okay, how do you add two matrices? How do you multiply two matrices? What is REF? Then also we talked about
Ma'am, screen is not visible.
Not visible.
but it is showing that you are sharing your screen. It's not visible.
Your screen is coming black for us.
Yes, black.
Yeah, it's completely dark.
I think your PPTs are got forwarded to next page.
Oh, ठीक है. Yeah. I think it just give me 1 second, huh? Okay, I'll do this. Okay, I think I'll disconnect this. Just
Ma'am, can you start with positive definitive and positive semi-definitive?
okay, from there on. Okay, so REF also I need to repeat. Is it
No,
so?
I just saw, I mean, I read an article about that REF, and saw that this REF is used for dimensionality reduction where some of the features may be redundant. So is this something widely being used, or because there are other methods, say, to say that a particular feature is statistically significant to decide if that has to be included in your final, let's say, feature vector for before training, right? So is this being widely being used, or there are some other methods like SVD or based on statistical
SVD.
significance we
Yeah,
typically do?
actually REF is. I hope you can see the screen right now.
Correct, yeah.
Yes.
Okay. So we'll start with REF because it is very important. It is used everywhere. Linear independence. Linear independence you require for PCA, principal component analysis. Because REF is being used to find inverse, find the determinant everywhere, finding the system of solving the system of linear equations. Okay. Is it okay? Hello?
Yeah. So
Yeah, ma'am.
Yes, ma'am. Yes.
Yeah, it's okay. Yeah.
So we saw, okay, we'll do one example. REF, you remember, right? Or should I need, do I need to, we'll do this example just to revise.
No, we just have some rules,
Let's
right?
just have a
Where
recap for
that
this.
we just have to follow and make sure that there will be one leading, let's say, entry
Can
and
we
then
make it,
followed
ma'am?
by zeros.
Quick recap,
Uh-huh.
ma'am.
Yes,
Yeah,
quick,
okay.
quick recap.
Okay, so we'll have, okay, positive definite is just after that only we started with this REF. So we had,
Yeah.
we want in REF that all the zeros, like row containing the zeros, all zero, it should be below any other row. So that is, so this is, see, the zero row has to be at the bottom. Okay, we have to make ensure. And the first non-zero entry in each row is called leading entry. So for example, here, this is a leading entry, first non-zero entry. Okay, this is the leading entry of row 2. This is the leading entry of row 3, and so on. This is the leading entry of row 4. Okay, so these are the leading entries. Now it says that each leading entry of a row is in the column to the right of leading entry of row above it. For example, here, leading entry of row 2 is 4, and it is on the right of leading entry of row 1, right? Leading entry of row 1 is 3. So to the right of 3, you have the 4, which is the leading entry of row 2. And also, -4 is the leading entry of row 3, non-zero, first non-zero entry. And it is on the right of the leading entry of row 1 as well as 2. -4 is on the right of both 3 and 4, which are the leading entry of previous row. Similarly, 6. 6 is on the right of -4. 6 is on the right of 4 also. 6 is on the right of 3 also. So the idea is the leading entry of any row is to the right of leading entry of the previous row. Okay, so this is the concept. So you have to, if it is a square matrix, so this is a square matrix. So REF form will be a upper triangular matrix. Upper triangular means the entries below the diagonal have to be zeros. Okay, so let's see how we did one example also.
Yeah, ma'am, if you go to
ma'am.
that example, the third column, in the third column, it's not in the third row, right? It is you have the leading entry in the second row, right? If you go to the earlier
This
page.
example now.
No, I think the one before.
The
I
one
think.
which you were
example.
showing.
Yeah, the one
This
you
one.
are showing.
This one.
I think the one before, okay. So
Okay, let's see for this example. Let's do it. Okay,
okay.
you will do with me. I hope you have copy and pen with you. Let's do it. Okay, are you with me? Huh?
Yeah.
Yeah.
Okay, so the
Yes.
first task is convert. This is the leading entry of row 1. Okay, now your task is to convert all the entries below this leading entry to 0, because you have to, this is the square matrix. So you have to make it upper triangular. That means all these entry, make it 0. So first task is make the entries of column 1 as 0 below the leading entry 1. Below 1, make this entries as 0. How will you do it? This is row 2. So you say row 2 minus 2R1. R2 is, what will you, what operation will you apply to make it 0? This is 2, right? R2 is, please mute.
Negative.
So R2 is R2 minus 2R1. Okay, so this is R2. R2 2 minus 2. If you do it, only then you'll get 0. So you say R2 is R2 minus 2R1. So you get 2 minus 2 is 0. 4 minus 2 into 2 is 0, because this is 4 minus 4. Then 0 minus 2 is, I'll just use the laser. Then 0 minus 2 is 0. Or 0 minus 2 is minus 2. 6 minus 3 into 2 is 0. 2 minus 2 is 0. Okay, you got this correct?
Yes, ma'am.
And now you have to make this entry as 0. How will you make? Because you want to convert all these entry to 0. So you have to take, operation with respect to R1.
R3 minus 3R1.
R3 minus 3R1. So 3 minus 3 is 0. 6 minus 2 into 3 is 0. 1 minus 3 is minus 2. 9 minus 3 into 3 is 0. 3 minus 1 into 3 is 0. Got it?
0.
Yeah.
Yes.
Now, what operation you will apply here so that this entry turns out to be 0?
R4
So-
Minus.
R4 minus
What will
R1.
you? Yes, R4 minus R1. So 1 minus 1 is 0. 1 minus 2 is minus 1. 0 minus 1 is minus 1. 2 minus 3 is minus 1. 1 minus 1 is 0. All right. Now, with
Right.
what? Yeah. What will you apply here? This
R5 minus 2R1.
R5 minus
Ah.
R1. Yeah.
R5, this is 2. So R5 minus 2R1. So 2 minus 2 is 0. 3 minus 2 into 2 is 4 is 0 minus 1. 1 minus 1 into 2 is minus 1. 5 minus 3 into 2 is 5 minus 6 is minus 1. 2 minus 1 into 2 is 0. All right. So
Madam, can't we
now
do R5 minus R2?
R5 minus R2. You can do it, but we follow this practice
Okay.
that since you are converting all the entries below row 1 or like the
Mhm.
first column to 0. So you
Mhm.
have to apply the elementary row operation. You have to subtract, the constant some multiple of R1. This is the practice, because if you do implementation programming, then
Okay.
you have to follow something, systematic.
Mhm. Got it. Got it.
Ma'am,
Okay.
when we're calculating, we're referring to to the same row, right? Like here, we are referring only row 1. Then based on row 1, we are trying to evaluate other and make it 0, right?
Yes, correct. But
Okay.
now, okay, so this is the
Madam,
pivot.
ma'am, one question was that that R2 was already converted. R2 was already made to R2 minus 2R1 in the last step. So in the for R5, what will be the means if someone asked that it will be, we can do it R5 minus R2. So we will take the original one or the one which we just did R2 minus 2R1, the last one.
You're
So
talking about step 1.
in first step we already have converted R2. So that was my question, that
So in the next step, this will be followed, not the previous. Now you have to perform operations on this. Okay.
Yeah.
Okay.
No, I think
So-
he's asking about the sub steps, right? In the one step, we are doing all these operations, right? So
Yeah.
in first step, we have changed the 2 to 0, right? So as my question was that can we do R5 minus R2 or R2, right? So but the
Minus
R2 already become 0. So
yeah, R2 has already changed. So how
right,
can
right.
we use that R2? It is already
right.
changed.
Right.
But
Got
in
it,
the
got it.
same step, we are not using R2 again, right? So I think in a particular step, we can change only one row at a time. So if you see in the step 1, we are not changing or using R2 anymore after the first particular thing.
Right. That's right. Yeah.
Yes, that's right.
Got it.
So,
Okay.
ma'am, one question. In elementary row operation, is there a subtraction is also an elementary row operation?
Yeah, this is elementary row operation now. You are doing this is elementary row operation. What is one
Think
operation
you
is
can add or subtract, right? Let's say you can multiply it with a constant and subtract from another row or add from the another row to get 0.
Yeah, I think in the previous slide there was only mention of addition.
Yeah, that
That's what I
depends.
said.
It depends on the matrix actually.
addition, subtraction, both work.
If we want to achieve 0, then we need to add addition or subtraction.
Yeah, there are some
Yes,
rules,
yes.
right? You can either swap or you can multiply it with constant, or if there is already a 0
Yeah, these are
for all the row,
element-
that can be moved down.
Correct. Here I think
Yeah.
the subtraction is same.
These are the rules. So you can interchange two rows. You can add the constant multiple of one row to another row. Constant can be,
Positive or
negative
negative.
number also.
Yes, makes sense. Yes.
And you can multiply row by some non-zero constant also. This is also row elementary operation.
Correct.
Okay,
Yeah.
moving forward. Now we are at this position. Okay, but now,
Ma'am, can you repeat why for R5 step, why we are not doing R5 minus R2, rather we are doing R5 minus 2 R1?
R5, okay. So so what I'm suggesting is you have, if you have to implement, right? See, by human eye, okay, you can see this can happen. You can perform R5 minus R2, you'll get here 0. Okay, but if you have to do implementation, you have to be, specific. You have to follow some, steps. So first step is always you have to, like R2, R3, whatever rows are below row 1. So what you have to do is to this, any row below row 1, you have to add to these row a constant multiple of row 1. Okay, in the second step, what you have to do, second step, you are here. Okay, but here you are getting 0. So you have to just swap it with some non-zero, because here the leading entry has to be some non-zero. Okay, so then after swapping, what you get, you are swapping R2 with R4. So you can swap R2 with R5 as well. But now now what is your task? Your task is to convert all these entries below this leading entry to 0. Then now you
0.
cannot perform any other operation. So you have to not deal with these entries. So now what row operation will you apply? But these are already 0. But now what about this? So you have to subtract. You will say, okay, R5 is, see, R5 is R5 minus R2. You cannot use any other. Okay. Suppose here also, suppose if you have minus 1. So I'll tell you the logic. You are asking, what's your name?
Megha.
Megha, if I suppose say here also entry is minus 1. So you can say, ma'am, if I want this entry to be 0, I can say R5 is R5 minus R1. But what will happen? This entry, this is 0. So this will become minus 1 because of this entry, right? So the only logic is you are here in the row 2. So the leading entry is you are resolving for row 2. Okay. And it is present in column 2. So you have to see, you have to make sure that all the entries below this leading entry minus 1, you have to convert it to 0. See, these entries are already 0. So only operation you have to apply is this, let R5 is R5 minus R2, because you are looking at the leading entry of row 2. Okay, so now you have to involve the row 2 only, because you are looking at leading entry this minus 1.
Ma'am, I have one
Clear.
question. In our after step 1, in row 2, we have 4 zeros. In row 2, after step 1, in the upper step, yeah, we have 4 zeros. So we had yesterday you told us that we shall try to bring that 0 rows to the last one. So ideally we should have interchanged row 2 with row 5, right?
You can interchange row 2 with row 5 also, not a problem. Not a problem. Row 4 is also valid. Row 4 is also valid candidate. Row 5 is also valid candidate. Okay, you can do any. So you can interchange row 2 with row 5 as well. That's also a valid point. Okay.
Okay.
Ma'am, one question I have. When leading character is there 0, we can't interchange with R2 with R3.
No. Leading character cannot be 0 now, because leading character is the first non-zero character, first non-zero number in that row, and it is
Okay.
so we want leading entry to be here. So we are, that's why we are swapping it with the some row which has leading entry in column 2.
Okay. Thank you.
Ma'am, as you told last time, there is no rule like that non-zero entry should be immediate of the last row. So here in second row minus 2 will be is there. So that will be, can we treat as a leading entry instead of swapping again?
No. Here, what are you saying? Actually, you are right. Your question is very much valid. Okay, so here leading entry is -2. Here also leading entry is -2. But the leading entry of row 4. What is the leading entry of row 4? -1, and it is on the left of the leading entry of previous rows. Okay, so that's why. And as per our REF definition, we want that leading entry of any row should be on the right of leading entry of
Right side.
previous one. Yeah.
Hmm.
So that's why we have to swap. Okay. Is it okay?
Yeah, got
Yes,
it, ma'am.
ma'am.
Yeah.
Okay. So now the thing is we do. Okay, we have interchanged row 2 with row 4. I'll use laser pointer. We interchange row 2 with row 4. We get this. Now these entries are already 0. Now we have to make this entry as 0. Now what row operation will I apply? Elementary row operation. Now this is with respect to R2 we are considering.
R5 minus R2
R,
minus
Huh.
minus plus.
R,
That
Yeah,
becomes 0.
R5 minus, correct.
R2.
R5 minus R2. So you get, what you get? -1 plus 1, 0.
0.
Yes. -1 plus 1, 0. Then -1 plus 1, 0. So see, the last row is all zeros. Okay. Now tell me, what should I do? Now we look at row 2 is sorted, row 1 is sorted, like leading entry of row 2 is sorted, leading entry of row 1. Like our task is make the entries below the leading entry to be 0. See, these are all entries you have turned out, you have made them 0.
Row with
All
index
these
3 needs
entries.
to be 0 here. Huh?
Now, yeah. What are you telling?
Row with index 3. The
Yeah,
third column should
correct.
be 0 here in this case. Yeah.
So now our task is not, we have to look at row 3. This is the leading entry. Now your task is to turn the entries below this
0.
leading entry
0.
0. How will you
R4
make
also
it? Tell me,
0.
which operation will you apply? Now this leading entry is present in R3. So
R4
whatever.
minus R3.
R4 minus R3. Yes.
Yes. So you've got, now see this.
So ma'am, just a question here. So because we got all these rows 0, right? So can we say that if I consider this as a, let's say, a feature vector, so a particular index where we have all the entries are 0. So this, can we say that this is a redundant row
Very
which
good.
we can
Very good.
eliminate?
I'll explain that also. That linear independence. So see this. So see, you have two rows. They are at the bottom. Okay. So what are the number of non-zero rows? Can you tell me? What is the number of non-zero rows here?
3.
3. So you will say, what is the rank going to be? It's going to be
3. 3.
3.
So rank is 3. Good. So if you understand this point, REF, you can solve so many problems.
Regardless
Okay.
of
Now,
what I have one question here.
Practical.
Regardless of whatever the operation we do, will we end up with the same final REF, or can we
no,
end up with a different
REF may
REF?
not be. No. REF may not be unique.
Okay.
Okay. RREF is unique, but REF is not unique. Okay. Okay. Now let's look at some determinant, and I'll.
I'm
Yeah,
sorry
yeah,
to
yeah.
interrupt.
Please. Yeah.
What is the practical implementations of REF?
Practical implementation, I told you, it is used to find, whether your feature vector. Suppose your feature vector, right now I'm not remembering. Okay, suppose salary and income tax is there. Actually, REF is used in many things, to calculate whether the two features are linearly independent or not. For example, take salary and income tax. There are two features. Okay, suppose there is a person. Okay, you want to bank wants to predict whether the loan should be given to that person or not. So bank is taking all the details of, say, 1,000 customers. 1,000 customers, they have applied for the loan. So for each customer, they are saying, okay, show your salary, show your income tax, show your qualification, show your designation. So all these are features. Okay. But the thing is,
Right.
if the salary is very high, the income tax will be very high. Right or not?
Right.
So you can say income tax is very much dependent on the salary.
Right.
Right? So they are dependent, you can say. And REF will also help us find a linear independent feature. We don't want, if the features are dependent, so they'll have redundancy in them. You will have redundant information, which you don't want, because it will take your time, computation time will be higher and all that. Okay, so REF also tells, okay, suppose this is your salary. First column is salary, second column is say, okay, so here second column is loan, you can say, third column. Okay, first we have to find which are the linearly independent. That will come to it, just wait for a while. So REF is useful for finding the inverse of a matrix. It is useful for finding the linear independence, which is further
Or
useful
yeah,
in
the
finding the
multicollinearity, right? We can say
multicollinearity. Correct. We'll look in PCA. You will study after mid-sem. So PCA is very much important, because if you have say 10,000 features, so 10,000 features all will not be useful. So you need to have so this 10,000 feature space, it will get converted to, you'll transform it into 100 features, and they will be linearly independent. Okay, and REF will help you. It will tell you, okay, which column, which feature vectors are linearly independent. So that's the
So we are basically
application.
filtering out the data in layman point of view based on the all. So we are basically filtering out the data based on all this logic, like linear independence, REF.
Linear independence. I don't want to burden you always with this concept right now. We'll see in the
Got it.
maybe today.
Ma'am.
Today we'll definitely see.
Okay.
Okay, linear independence. But
Ma'am,
for
what
time
is R
being,
is equal to 3? What does that mean?
oh, okay. This is the rank. Rank
Rank.
is, it will tell you. Okay, rank. Rank is the number of the non-zero rows.
Non-zero rows.
Rank,
Okay.
rank also tells you the number of linearly independent columns. 3
Okay.
independent columns. So 2, you can say there are 3 independent features, and which are these. This one, and this one, because they contain the leading entries.
Right.
So
Okay.
these 2 columns are dependent. I'll tell you, just
Sure.
digest this concept that rank is equal to the number of non-zero rows in REF. So which is
Okay.
3.
Okay.
Okay.
Thank you.
Okay, now we'll go to the determinant formula. So determinant is like AD minus, if you have 2 cross 2, so just multiply A into D minus P into C. Okay, this is your determinant. Okay, now if you take one example like this, so it's like 3 into 4 minus 5 into 2. So 3 into 4 is 12 minus 5 into 2, which is 10. So determinant is 2. Okay, so 2 cross 2, very easy. Even 3 cross 3 matrix, it's very easy. What do you do for 3 cross 3 matrix? I'll tell you.
Ma'am, can you please go back to the previous slide for a 2 cross 2 matrix?
Yeah.
Ma'am, the formula we know, but what exactly is this, ma'am? Determinant?
Determinant will tell you whether the matrix is invertible or not.
Determinant A equal to, is it determinant A equal to
Of a
AD minus
matrix.
B?
Huh?
Determinant A equal to AD minus BC, right?
Yeah. Determinant
Yes,
of
yes,
A.
yes,
A is a matrix. Now, what is the importance? Let me tell you why. So basically, so determinants are very crucial in machine learning for determining whether the matrix is invertible or not. Okay, so if your matrix is invertible, the determinant will be non-zero. So here, that means A is invertible. You can find its inverse. Okay. So this is the...
No, someone asked that what is the relevance of this? The determinant equal to 2, that what does it, what is its relevance?
Determinant is 2 means this it is non-zero. You just say that, okay, this matrix is invertible. It is, since the determinant is non-zero. That's it.
Ma'am, can you explain what does it mean when you say it's invertible?
I'll come to that inverse also. So invertible means if you have a matrix A, okay, and if you multiply with B such that AB is equal to BA is equal to, you get I, identity matrix. Identity is this matrix. You know identity?
Yes,
1,
leading
1, 1
diagonal
in the diagonals.
in leading diagonal.
A of ij is equal to A of ji, right?
Huh?
A of ij is equal to A of ji, means if they are...
No. Invertible
Yes,
means
yes.
if you multiply any matrix A with matrix B such that AB is equal to BA is equal to identity matrix. Suppose A is 2 cross 2. So here, if you get this 1, 1, 0, 0. So this is identity. When you have 1 on the diagonals and 0 everywhere else. So here you call B is called the inverse of A. I'll come to it after determinant. I'll come to the inverse. So if A is invertible, that means if its determinant is not 0, then only this B matrix will exist. And B is called the inverse of A. So B is basically A inverse.
Ma'am, what would it mean if the determinant value is negative?
Negative, positive, whatever it is, it should be non-zero if you want the matrix to be invertible. Okay.
Okay, ma'am.
Ma'am, can you please repeat once again, please?
Repeat. Okay. So I'm saying that here, for example, determinant A, you are getting it to be non-zero. It's 2. It can be negative, positive, but it is non-zero. So it means A is invertible. So its inverse will exist. So you can write like this: A into A inverse is equal to A inverse. When you multiply inverse with A, you'll get identity matrix. So identity is this 1, 1, 0.
0,
I'll
0.
help you. So this A inverse is nothing but B. It's B. Okay. Okay. Now comes to the 3 cross 3 formula. 3 cross 3. I'll show you how REFs are very useful in finding the determinant. But let me just tell you what is the conventional way of finding the determinant formula. So this is what you do. You just take A, expand along, suppose row 1. Row 1 you take A, B, C. So A you take, leave out this column, leave out this row. What you are left with? 2 cross 2. So what is the determinant here? E into I minus F into H. Right or not? So that's why this is the first term. Is it okay? First term. See, we are calculating the determinant of now 3 cross 3. 2 cross 2 is very easy. 2 cross 2, what do you say? Okay. 3 into 4. So 2 cross 2 very easy. 3 into 4 minus 5
Minus
into 2.
5.
Huh? What?
Yes. No.
Yeah. So same logic we apply here in this. So what do you do? So here this is 3 cross 3. Now same formula will not work here. So what do? You take, suppose the first row. First element is A. So you leave out this column, leave out this row where A is present. What you are left with? Only these entries. Okay, I'll write. See, A is present here. Leave out this column, leave out this row. So you're left with 2 cross 2. Now you're finding the determinant is easy. E into I. So E into I here minus F into H. Okay. Next you go to the next element of row 1. So this is B. So here it is plus, you have to take alternate plus minus. So this is plus A, then you have minus B, then you have plus C. Plus C is the third. Okay, now with B, just cut the column where B is present, cut this row. What are the elements left? D. So you take the determinant value, D into I minus F into G. Okay, D into I minus F into G, right? So you get this. Now you take the third. Third is C. So plus C. Plus C. Now you leave out this row, leave out this column, you are left with this. Calculate the determinant. So it is D into H minus EG.
I didn't get why we have done minus B and then plus C. Why we haven't done both minus or both plus?
So it is, you have to take alternative plus minus. So this index is 1, 1. 1, 1. Right? So 1 plus 1 is 2. So it is even. So that's why you have taken plus. Now this index is, this is first row, second column. So index is 3. So here you have to take minus 1 to the power of 3. So which is minus. Okay, so here you have taken minus 1 to the power of 2. Minus 1 to the power of 2 is 1. Right?
Ma'am, is in your example, it is minus 1 only in the example.
Exam?
In the below example,
Okay,
for
sorry.
1, it is showing as minus 1 only.
No, it's equal to.
It is equal sign.
Equal to.
The base
That is
dash
equal.
That
The
is
second
No,
line
it is
greater.
coming as minus 1, minus 24. It is showing. It's
No,
showing
that's
minus 24, right?
That's just
No, that is equal actually. The print is not proper.
Sorry.
Printing problem.
Actually, it is equal to. Sorry, Justin.
Okay. So got it.
Okay, now you can solve this.
No, okay. Now got it. I was thinking that as minus.
No, actually, I'm sorry for this, light. It is too light now. I'm sorry.
And that's okay.
You are
That's okay.
Okay. Thank you.
So first
Okay,
one
now
will be positive, second one negative, third one again positive.
So you have to take alternate plus minus. Okay.
Got
Plus, minus, plus. Okay. Now we'll do this numerical. Okay. Now here 1 into you leave out this column, leave out this row. So what you get 4 into 6 is 24.
24 minus 5.
24 minus 5 into 0. This now. Okay. Next, you have to take this 2. So you have to take minus 2. Okay. Now what will you do? Take minus 2. You leave out this column, leave out this row. What will you get? 0 into 6.
0,
5, 1.
1, 5.
Minus 5, 1.
Minus 5 into 1.
So
this term is nothing but 0 minus 5. Okay. Now go to this. This is plus 3.
0.
Leave out this.
Into 0 minus 4 into 1.
Minus 4.
Now you just have to solve. That's it. So the determinant is non-zero. So
10 plus 10.
minus 12.
Is it fine or any doubt?
Yeah, fine.
So, ma'am,
Fine.
if
Only
I
one
have a
question.
doubt.
If determine
The answer is
I
22.
have a
What
doubt.
does that mean? It will have identity matrix or not?
What?
Answer is 22, non-zero. So what does that mean?
So that means it's this matrix will have inverse. Its inverse will
Okay.
exist. Okay.
Madam, just one question here. So if we say a determinant is a positive value, that means no multicollinearity exists, right? So can we say that?
If
Or
determinant
is a positive value?
positive or
That means it is invertible, and there will, and your RREF will also not have any zero rows.
even if it is negative also, still it is going to be invertible. I'll show you.
Okay.
See whether determinant is positive, negative, whatever it is. If you want it to be invertible, it should be non-zero. It can be positive, negative. Okay.
Okay, it should be non-zero. That's what they're saying. Okay.
Ma'am, I have a doubt. Can we calculate the determinant for a 3 into 4 matrix?
Yeah, I know your question is will be that. So I already have the slide ready. Okay, so determinant of 4 cross 4 matrix. So what do you do here? You start with A11, A11 into, now you have to multiply, you just leave out this row, leave out this column. So you find the determinant of this. Okay? Because earlier you were finding the determinant, like when you calculate the first value. So for example, if you have A, so then you are leaving out this column, this row. So you are calculating the determinant of this, E into I minus F into H. Same thing you have to do for 4 cross 4. So this, what is the determinant of this? This is A11 into M11. M11 is a 3 cross 3 determinant of this. Okay. Then you have to take minus A12. So then you have to take minus A12 because it is alternate plus minus. Okay, then you will leave out this column and this row. Okay, so you leave out this column and this row because A12 is present here. Okay, so what is the 3 cross 3 matrix? A21, A23 and A24, you are left with this. A21, A23, A24, A31, A3. So you have to calculate determinant of this. This is M12. Okay, so likewise, now you go to A13 plus A13. A13, when you have A13, so what do you do? You leave out this row, and this column. So what matrix you are left with? A21, A22, A24, A31. You have to calculate determinant of that. So this is nothing but M13. Okay, and so on. Minus A14. Then you have so last entry is A14. So you just cut it out. What entry you get? What 3 cross 3 matrix. So now you have to find the determinant and then multiply with A14. Okay. So now see, this is going to be like too much not complex, but it is very tedious, boring calculations. Let's do something easy. Do you agree? You want something something very handy thing, right?
Simplified way. Yeah.
Okay, so this is calculating. You can have a look at it later. This is just using the conventional way to find the determinant. But we want simple things. Okay, we say
Ma'am,
that
determinant is only for a square matrix, right? Either a 2 cross 2, 4 cross 4, only square matrix.
Yeah, determinant is only calculated for square matrix. Square matrix means where the number of rows is equal to the number of columns. Okay. So very valid point, very good point you raised, that determinant is only calculated for square matrix. Okay, this is the calc. You can see you have to just substitute. Do you want me to do this? Just substitute the values. That's it. You want me to do, or you want me to show something simpler way of calculating determinant?
Yeah, let it be simpler.
Simpler.
Okay. So if you have any like n cross n matrix, not just 4 cross 4, so you have to use this elementary row operations. That means to any row, like any ith row, add to this a constant multiple of any other row. K can be negative, positive, whatever. Okay. So if you do not do any row swaps, so basically after having these row elementary operations, performing these row elementary operations, you get into the REF form. REF form, after getting the REF form, just find the product of diagonal entries. That will be your determinant. Okay. And if you do one row swap, just multiply the determinant by -1. And if you do two row swap, then sign becomes positive again. Okay. So I'll just take this, this information, and this is valid for any n cross n determinant. Let's see this. So you have B with you. B. You can see B matrix. Are you ready? Okay. So for converting into REF form, first task is, this is the leading entry of row 1. Convert all these entries to 0. How will you do it? Again, you apply the row elementary operations with respect to row 1. So for example, R2 is R2 minus 2R1. R3 is R3 minus R1. And this R4 is R4 minus 3R1. So this is row elementary operations you apply. So all the entries below 1 is you are getting 0. Now come to row 2. Row 2 leading entry is this. Again, the next task is convert all the leading entry, convert all the entries below this one to be 0. Below this leading entry to 0. That means convert this to 0, convert this to 0. Again, now here you are talking with respect to the leading entry which is in row 2. So here you have to apply the row elementary operations with respect to row 2 only. That is R3 is R3 plus R2. If you add these two, only then you will get 0 here. Similarly, R4 is, what should you apply here so that you get 0? So R4 is R4 minus R2. So you get this. Okay, 1 minus 1 is 0. 1 minus 1 is 0. And -1 plus 1 is 0. 2 plus 1 is 3. -1. Now you tell me. You have got upper triangular. This is REF. You will stop here. You have got upper triangular matrix because this is a square matrix. So for square matrix, if your REF is upper triangular, you are done. Okay, now find what is the determinant. What is the determinant? It's just the product of diagonal entries. 1 into 1 into 3 into 1. So this is your determinant.
So if any row has all zeros, how would you do it?
If row, so in R, if you have REF form and if the last zero, so only last zero will be 0.
Yeah.
So then what will, now you tell me now, what will be the determinant then?
0.
Because this 0, if suppose this is also
so the
turns out to
determinant will become 0. We can still,
be,
okay.
yes, correct.
Okay.
The inverse will not exist. Okay.
So you can see,
Okay.
tell me.
You said row echelon form is not unique. So can this determinant value change as well depending on how you reduce it?
No. Determinant will be always one value unique. Because here, if you say, if no row swap, because see, if I multiply this row by -1, suppose it's still in REF form, it still is in REF, right?
Yes.
So REF may not be unique, but determinant is unique. Because if you just multiply any row, I have this formula that if you multiply any row with a constant, the determinant also gets multiplied with that constant. Okay, I'll come to it. It's good that you are asking questions. Okay, got it. And if you swap any row, two rows, so what will happen? you have to multiply the determinant by -1. If you just do one row swap. So for example, if you here it does not involve any row swap. But for example, so suppose this entry is 0. Suppose. So then you have to swap it with third row, right? Because leading entry of row 1, this has to be non-zero. So then suppose there is just one row swap you do. So in the end, what will you do? You'll multiply the determinant by -1 as per this rule. If one row swap, multiply by -1. If there are two row swaps, then you again multiply by -1. So its sign will again be positive, right?
Correct. But see, if the determinant is 100 or -100, we can still say that that feature vector is numerically stable, right? So is there any other, let's say, thing that we can infer from that minus, from the overall output?
Okay, you are saying that
Because if it is +100 or -100, we can still say that it is numerically stable vector, right?
So right now we are not talking about determinant having negative or positive value. We are just saying that
Okay.
like if determinant is non-zero, then it is invertible.
Right. Okay.
So basically, a positive determinant just signifies that linear transformation. It preserves the orientation of the space. So right now, let's not. So geometric interpretation is this: like a positive determinant means the transformation does not flip the space.
Yeah, that means it is only stretching. It does not squash the data if it is close to 0. That means we will not be able to bring it back to its original form mathematically.
Yeah. So this all of these concepts, you will learn when you are doing eigenvalues. So product of eigenvalues is also determinants. There you will learn, positive, negative. What does this imply?
Okay.
Ma'am, I understood. I mean, we'll have to get the matrix into REF, and then we'll have to use the product of diagonal entries to get the determinant. But what does that first? Can you go back to the first slide where you mentioned the formula? So to make 0 below pivots, what exactly? Use only that formula what you've mentioned, right? I'm not able to understand. And
so this is the row elementary operations now. It is row elementary operation R1. So for example, this R2
okay,
is
you're
R2
doing
minus. Yeah, this is the same row elementary operation. So it says use these operations.
So then what you have mentioned. So once we will have to get the matrix into REF, and once the matrix is in REF, then points what you have mentioned. If no row swap, one row swap, two row swap, that we'll have to apply on that.
Yeah. Correct. So after getting REF,
because for getting into REF, we'll have to do the row swap, right?
It's not necessary. Sometimes you may need to do. For example, in this example, we have done row swaps, right?
If the first value is 0, then only we need to take for the swapping, right?
Correct.
Yes.
And even in cases like this, so here also you did row swap. You this one row swap, right? So you'll multiply the determinant at. So here you only did one row swap in this whole REF calculation. So at the end, what will you do is you'll multiply the determinant value. Determinant here is the product of diagonal, but here the product of diagonal is again 0. So ultimately, suppose it is non-zero. Suppose then at the end, when you find the product of all these diagonal entry, you have to multiply by -1 because you did one row swap. Okay.
Ma'am, do you have any example for this row swapping part?
This is the example. Now I told you. Here I have done row swap because this is the leading entry is here, and it is on the leading entry of row 4 is on the left of leading entry of row 2 and 3. So which is not in REF form. Because REF form says that leading entry of row 4 or below row should be on the right of the previous row. So this is violating. That's why we swap.
Yeah. So first row swap, we say -1, then the second row swap, we say positive. It becomes positive, or it alternates
Because you
between.
again multiply by -1,
Correct.
now.
Yeah.
Right. So it will be
So
positive.
correct.
So why
All
are we
right.
multiplying by -1, like in case there are any row swaps?
What? Come again? Okay, I'll tell you why you are multiplying by -1. This your question?
Yes.
I'll tell you. Here, I have this property. Now I'll take one example to illustrate it. So let's see all these properties and we'll see one example for all of these. So if you take the product of two matrices, okay, so then you calculate the determinant. It will be equal to determinant of first matrix into the determinant of second matrix. Okay, let's see this property. So determinant of A is equal to, can you see the first line? Okay, now you'll be able to see. Determinant of AB is equal to determinant of A into determinant of B. Suppose determinant of A you calculate 1 into 4 minus 2 into 3. So it will be 4 minus 6 minus 2. Determinant of B is 2 into 3, 6 minus 0 into 1, 6. So now you calculate AB product. What is the product? 1 in, so what is, how you get this value? This is 1 1. So that means first row of A take its dot product with the first column of B. So 1 into 2 plus 2 into 1. So it's 4. Now, how do you calculate this value? We did it yesterday. I'll do it again. No problem. So this is 1 2 entry. 1 2 means first row. This is first row and the second column. This, right? So you have to take this entry. This is the index we are saying, not 12. Don't read it as 12. This is 1 2 index. So this is first row of A. Take the dot product with the second column of B. First row of A is this. Take its dot product with the second column of B. What will you get? 1 into 0 plus 2 into 3. 6. So you got 6. Now take this. This is 2, 1.
I think this is clear, madam. So
Acha, this is clear. Thank you.
yeah.
Ma'am,
Okay.
please, no, ma'am, it's not clear. If anyone is clear, please let other know this. I
it's
know
fine.
few of them already aware of it, but please don't stop the session in between.
Okay, go ahead. Yeah.
Okay. So what is this entry? Huh? What?
Can you complete that first use case using the row elementary operation for that matrix? What will be the determinant for that?
Acha, you are saying do row elementary operations to find the determinant. Is that?
No, not this. The last example where we are having the not 4 cross 4 matrix. Yeah. For this one. Yeah. So
You
I
have
want.
completed now?
Yeah, we have completed till now, but the multiple diagonals was there where the row swap. So
There
that
is
example.
we did not do any row swap now.
Not
There
here.
was
Like
no.
other examples, if we have.
Acha, ठीक है. Got it. This you
So
were
yes,
talking
for
now.
this example, what will be the determinant value for this one? So it will clarify everyone's doubt using the both like all the properties of determinant.
This
You
is
tell
0,
me
right?
what?
This is 0.
Yes, it is 0 because the product of diagonal entries are 0. What is diagonal here? 1 into -1 into -2 into 0 into 0. This is diagonal now.
Correct. Okay.
So
But are we not?
determinant.
But are we not? I mean, removing the last two rows.
No. We don't need to remove any rows. See, what is
Okay,
the
only for rank we'll have to ignore the last 0 entries.
rank is just the number of non-zero rows.
Non-zero. Okay.
Yeah. Okay. Okay. One more point I want to say. So what can you conclude? how will you link rank with determinant? Can you say if rank is less than n, where
Less than
matrix
row.
is n square,
Row.
then determinant is 0.
Yeah.
Because you'll have one row of zeros now. One row of zeros means, okay, I'll tell you about this. I'll link rank with determinant. Okay, just wait for a time being. Okay. We were doing the first property. Where were we?
So we
First
have to
property.
find 3 into 2 plus 4 into 1, which becomes 10 here. 3 into 2. 3 into 2
Yeah.
plus 4 into 1.
3 into 2 is 6. 4 into 1 is 10. So this is this is 10. Now how do you get this row? This is 2 cross 2 comma 2. Index is second row, second column.
Yeah,
So you
3
have to
into
take
0 plus
3
4
into
into
0
3,
plus
12.
yeah, 12. Okay. Now what is determinant? 4 into 12. You can use row elementary operations also to find the determinant. Not so it is up to you. Okay. 4 into 12 is 48 minus 6 into 10. 48 minus 60 is minus 10. So determinant of AB is minus 12. And we want that, okay. Now we'll see what is determinant of A. You have calculated as minus 2. Determinant of B is 6. So determinant of A into determinant of B is also minus 12. So you have basically validated. They are basically formal proofs also, but right now we are just focusing on understanding the concepts and properties. That's it. Okay. Non-zero determinant means inverse always exists. So here determinant is non-zero.
So A into A inverse is equal to identity matrix. That's minus
So
here,
we are
madam. That's
saying that, okay,
confusing.
yeah. What?
So,
What is
no,
confusing?
A into A inverse
Yeah,
minus
yeah.
identity matrix is what here saying.
Minus, no.
No, that's
Sorry.
equal, right?
It's equal,
That's equal.
equal.
No, that's
Okay,
confusing everywhere.
Everywhere. So here I just want to say that there exists in this matrix. I'll tell you how to find inverse. Just hold for a while. So I'll say, okay, A is A inverse. A into this matrix is giving you I, which is identity matrix. Okay. So this matrix is the inverse. How you calculate this inverse, I'll tell you after studying the properties of determinant. Now, third property. Two rows equal means determinant is 0. Two rows equal. What will you suppose here? Two rows are equal, right? How will you get 0 here? Can you tell me?
1 into 2,
do
1 into 2 minus 2 into 1, 0.
So what do? You apply row elementary operations. You say R2 is R2 minus R1. You agree or not?
Yep.
R2 minus R1.
So determinant is
Then
0.
what will you get? 1, 2, 0, 0. Now what is the determinant here? Determinant last row is 0. If any row is 0, determinant is 0. Why? Because determinant why it is 0? Because it's a product of diagonal entry. So 1 into 0 is 0. So matrix is singular. That's why we said now here. Here we could see that if any row, if there exists at least one row, which is row of zeros, then determinant will be 0. Because that entry 0 is coming in the diagonal. Okay. So we are done with this property, first property, second property, third property. Now you ask, one of you asked, I think Megha asked, if Ri and Rj you are swapping two rows, why determinant gets minus sign? Now I'll tell you. One of you asked.
Ma'am, one question on this third point. This also holds true for a bigger matrix like 3 cross 3 or 4 cross 4 if two rows
3
are
cross
equal.
3, 4 cross 2, any n cross n. So if you have any like REF of any n cross n matrix, you got one row as 0. So that one row, because that row contains all zeros. So that one
Okay.
zero is coming in the diagonal also, right?
Mm-hmm.
So that's why, and product of diagonal entries is zero, so determinant is zero. Okay. Is it
Okay.
okay? Third point. Hello.
Yes, ma'am.
Okay.
Yes.
Should I go to fourth
yes, yes.
property if you permit?
Yes.
Yeah, but that determinant in one slide, there was how we are finding the inverse of A. That you told you will show later, right? Inverse of A.
I'll show. Just wait for
Okay, okay.
after this
That's fine.
properties only I'll show.
Okay,
Huh?
okay, okay.
This third property, I hope everyone is clear.
Yeah.
Okay, now you go to the fourth property. It says that, see, I told you, now if you do any row swap, determinant changes sign. Now you are asking, you have very valid point that, okay, why determinant will change its sign? Why you are multiplying by -1? Let's see this. So this is your matrix A. Its determinant is -2. Okay, now suppose you change, you swap these two rows. So this becomes first row and this becomes your second row. Okay, now what is happening? Find its determinant. What you will get? 3 into 2 is 6.
Plus 2.
Minus 4. 3 into 2 is 6. Minus 4 into 1. So it is 2. But earlier it was -2. So you're by. So what are you saying? That if you are swapping the rows, then the determinant will get, you have to multiply the determinant by -1. So you're multiplying this by -1.
Does it hold true for 3 cross 3 matrix wherein maybe row 2 is swapped with row 3 or row 1 is swapped with row 2 or row 3?
Yeah, you can swap any row. But here we are talking about 2 cross 2, but you can talk of 3 cross 3 also. So if you do any row swap, the determinant will get multiplied by -1. That's it. Okay.
If we swap it for 2 times, then again it will be same, right? Like in the
So
3
again,
cross
if
3.
you swap, yeah. So if you swap it again here, for example. So here you again do swap.
Yeah, I
This
think in
becomes
2.
second row. So it will become the original matrix only now. So you
Yeah,
again
like
will
in 2
multiply
cross
by
2.
minus.
Yeah, it doesn't make much sense, but in 3 cross 3 or 4 cross 4, if it swap it twice, then the determinant should remain same.
Yeah. Even for if you do two, rows, if you do row swaps 2 times, then it will be as good as the original matrix determinant, right?
Right.
That's what you are saying.
Yeah.
Means not the same rows, right? If I swap one R1 to R2 and the next time I swap to R2 to R3, then that will be, in that case also, it determinant will be the same.
Yes,
Yes.
I can show you
Okay.
because we don't have time to calculate now. I'll show you in Octave. Let's take Octave, help of Octave, because you are asking down. It's my I should address. Oh my God, what to? This is the problem with so many ads. Let's see. Suppose A is 1, 2, 3, semicolon. Semicolon means go to the next row. 1, 2, 3 is your first row. Second row is 6, 9, 2. Semicolon means go to next row. 6, 1, 9. Okay. You get semicolon. Okay, not let's. Now let's swap. So this is run. Let me run this. Okay, A is this. Now suppose I swap first 2 rows. So new matrix becomes A1. Okay, let me calculate determinant. I hope this is just formula DETA. You don't have to. What is DETA? minus 149. Okay, now let me swap two rows. Now you tell me. Oh, you suggest now which row should I swap?
First with third.
Okay, I'll go with your first with third now. Okay, let me see whether we get. So this is your A1. Okay. Let's see what is the determinant A1. Okay, let me run it. See, this is determinant A1. You are multiplying the original determinant by minus 1. Now let's do again swap. Now you tell me what swap I should do. Whatever you'll say, I'll do that.
Now first with
Second with
second.
first with second.
First and second, okay. Now determinant of A1 will get multiplied with minus 1. So it will be as good as getting the determinant of the original matrix. Okay, so after row swap, you multiply this by minus 1. So you got 149. Now you are doing again swap. So you are again multiplying this by minus 1. So you get minus 149. Okay, is that okay?
Yes, ma'am. Got it.
Okay, ma'am.
All right. So don't get bothered with all these, This is the matrix. You are separating the rows by a semicolon. So this is the first row. Semicolon means go to the next row. This is the next row. Then semicolon next row. Okay. Okay. Now let's go to our slide. Huh.
Excuse me, ma'am. I have a question.
Yes, please.
You said that the determinants are only available applicable for square matrix, and determinants are used to find whether the matrix have an inverse matrix or not. So in that case, the non-square matrix won't have the inverse in any case.
Non-square matrix will never have inverse because you cannot find their determinant.
Okay.
Okay. Now, shall we move ahead?
Ma'am, I have a question. We will be having different REFs for a matrix. So is the determinant for that particular matrix after getting the REF would be same or it would be different?
No, it will be same. Determinant is always going to be unique. If you say, okay, REF will differ. Like you will say, okay, suppose you get one REF. Okay, now you say, okay, let me multiply last row with minus 1. So that is a valid row elementary operation. And then after multiplying by minus 1, that form, that matrix, it is still REF only, right? But only the determinant will get multiplied by minus 1.
Clear,
Okay.
understood. Yeah, thank you.
Okay. All right, now we say that determinant of a matrix is same as the determinant of the transpose. So it's valid for any matrix, n cross n. It's whether it's 3 cross 3, 4 cross 4, 5 cross 5, 100 cross 100. So if A is a metric, you find its determinant. It is going to be the same as its transpose. Transpose means first row will become your first column. Second row will become your second column. Okay, if you have n cross n matrix, first row will become first column, second row will become second column, nth row will become nth column. Okay, now let's find the matrix determinant of this A. What is the determinant? It is 4 minus 6, right?
6.
So it is going to be minus 2. Now, what is if you take the transpose? Take its determinant 4 minus 6. Again minus 2. So determinant of a matrix and its transpose, they are same. Okay, now row scaling property. So this is elementary row operation that you can multiply any row with a constant. This is one of the row elementary row operations. So what is happening? If you multiply any row with the constant, so this implies the determinant will also get multiplied with that constant. So for example, if you have this matrix, its determinant is this 4 into 1 minus 2 into 3. So 4 minus 6 is minus 2. Now you have the new matrix. You say, okay, let me multiply first row by 3. You multiply first row by 3. So it is 3 and here it will become 6. Now what? Now you calculate its determinant. So what will you do? You can use row elementary operations also to find the determinant. That's not a problem. So you say, okay, determinant is 3 into 4, which is 12, minus 6 into 3. 12 minus 18 is minus 6. See, original matrix determinant is minus 2. And once you scale the row 1 by 3, that means once you multiply row 1 by 3, 3, so it will change your original determinant by 3, like 3 times. So original determinant gets multiplied by, so its determinant is minus 6, which is 3 times of the original determinant. So what we have is this property. If you multiply, this is I basically. If you multiply any row with C, this is I. Okay, so determinant will also get multiplied with the C. That's what.
Yeah.
Okay, so you took, let me just use my this pointer. So here, this is your original matrix. Find its determinant. Now multiply the first row by 3. So you'll get 3 here, 6 here. So now you calculate its determinant. So determinant will be 3 times of minus 2. So you can find 3 into 4 is 12, minus 6 into 3 is 18. So 12 minus 18 is minus 6, which is 3 times the determinant of A. Okay. Now this is the summary of the properties. So determinant of the product of two matrices is the product of the determinant of individual matrix.
Yeah.
Determinant non-zero inverse exists. Equal rows, if the matrix has got two equal rows, so what will happen? Determinant will be 0. You have seen. If you do any row swap, sign of determinant changes. If you take transpose, the result is same. That means same determinant as the original one. If you do row scaling, you have to multiply the determinant by this scaling factor. That's it. So these are the row properties. Oh, these are
Ma'am,
the.
ma'am, I have
Ma'am,
one
can you
question.
please explain second one? Non-zero determinant inverse exist.
So I have it. I have it. Basically, first I'll tell you what is inverse. Okay. This I'll explain because one of you also asked.
Ma'am, in that slide where there was a mention like it is a product of all the diagonal elements, and after that there was another point that it will be if it is one swap, it is minus another. If you can go that slide, if you can just open, ma'am, that slide. Yes, yes. So here we are here we are multiplying rj with k. So here the determinant is not getting changed. We are multiplying with a constant, right?
You're talking about property 4.
Yeah, no, I am talking about property 6. Property 6, actually, when we are multiplying with a constant to any row, the determinant gets changed. So
Determinant will be multiplied by that scalar only.
With that
C.
constant.
Yeah.
Yeah. Now go back to that slide, ma'am.
Which slide? This?
No. That slide, which that three
Row
properties.
elementary. Correct. Row element. Previous. Yeah.
This one. So here we are multiplying rj with k. That's a constant, right? So here the determinant value is not getting changed. That's my question. Because this row elementary operation, we do we will obviously do this operation and we will multiply with -1, -2, 2. So it will not.
-2 nahi, -1. No, it's not -2. It's -1.
No, I am not talking about this second and third point. I am talking that as that determinant value getting changed when we are multiplying with a constant.
See, you are mixing -1 with a. No. Here you are talking about the row swap. Here you are talking about the one row is getting multiplied with the constant. This is different. That is
Yes.
different.
Yeah,
See, this is
I am talking
property
about
4.
0.6, ma'am. I am talking about 0.6 actually.
So
here we
0.6
are multi.
tell me.
So here we are multiplying with a constant and the determinant value is getting changed. So when we are in now, go back to that slide.
No, don't link with that slide now because you are bothered about 6th point and there
This
we are
is
not having
only the
0.6.
characteristics, right? This is the characteristics of the determinant. I mean, these are 6 different characteristics, correct?
Properties.
Yeah,
Means,
yeah.
I think in 6 point we can multiply by with any number, right? Other than 1. But in the first
Correct.
one, we are only multiplying only with 1, -1. So because of that, I think it is not changing its determinant value.
Okay. Actually, the thing is, here it is I, not J. It is I. This is also I. So here you are just saying if you multiply any row with any constant, then the determinant gets changed. Okay, by factor of C. That means, so you have A matrix. Okay, its determinant is say D. Okay, now you swap any 2 rows of A. So it determines. Okay, sorry. If you multiply any row of A with say C, so now determinant of A will get changed to now C into D. That's what it means. See, original matrix A has got say determinant D. Let the determinant value be 10. Okay, now you you take any row of A, multiply it with 2. Now you will get new matrix A1. And that matrix A1 will be its determinant will be 2 into the original
10.
matrix determinant, which is 10. So 2 into 10, 20. Okay. We have done this now here.
He's asking maybe like while finding out an REF matrix, we perform various row operations where we also like multiply one row with let's say some number like 2 and then we subtract it from another row and ultimately we find a REF matrix. So he's asking
Got
like,
it. But okay. You are saying okay. I understood.
No,
I
that is
understood
to
your point.
find the determinant itself, right? It's not cannot be linked with that scaling.
See, here you are doing the scaling. R5 minus 2 R1, R3 is R3 minus 3 R1. But you are not multiplying row 1 with 3 here. You are just doing the elementary row operations. Here I am not multiplying row 1 with 3 or 2, these constants. No. Row 1 is as it is. Okay. You are multiplying it and then you are adding it to another row. But you are not saying, okay, this is 2 R1. I have to multiply this with 2 and then make new row as okay 2 4 2 6 2. Is that what you are asking?
So, ma'am, with
Ma'am,
row
can I add?
transition, we do not get a determinant with a different value, is it? That value remains unchanged.
Determinant will
So-
always be unique, no matter what.
Ma'am, let me add one statement here. So the property talks about if there are, let's say there are two matrices, where the second matrix is having a row which is some multiplication of one of the row of the first matrix. In that case, the determinant of second matrix will be multiplication of the determinant of first matrix with the same constant. So it is talking about the
I
two
already told you
matrix.
now. So this is your original matrix. You multiply first row by 3. Okay, so this will become 3 and 6. Now you calculate the determinant of this matrix. It's going to be, since you multiply the first row by 3 here, Okay, the determinant of your this determinant of A1 will be 3 times. Determinant of
Correct.
A dash will be 3 times the determinant of A. So that is minus 6 only. You can see
Yeah.
3 into 4 is 12 minus 18 minus 6.
Yes, the doubt was, I think the question from someone was, they were mixing the properties with the one of the steps to calculate the RF. There are two different things. The
Yeah,
property
they are
talks
two
about the
different things. I hope, can I move if you permit? Move ahead.
Yeah.
Yes, ma'am. Yes, ma'am. Yes.
Okay,
Please,
okay,
please go
thank
ahead.
you.
Yeah.
Okay, now we have inverse. Inverse of a matrix. What is the inverse? So if you have a matrix A, such that when you multiply with A inverse, you will get the identity matrix. Now, what is the when can you obtain the inverse? It says that if the determinant is non-zero, only then the inverse will exist. So determinant is zero, that means it's a singular matrix. Singular matrix means determinant is zero. And in that case, there will be no inverse. Okay, if you have 2 cross 2 matrix, what is its determinant? Its determinant, how will you find? Just you have to do interchange these two entries. So here you will have D, here you will have A, and then multiply these entries by minus 1. Okay, and then you'll divide, you'll say 1 divided by the determinant of A. What is this determinant? A into D minus B into C. So this is the inverse. Again, it's very easy for, 2 cross 2 matrix. Okay, let me take one example. So this is a matrix A. At first you have to calculate the determinant because determinant is very much required here.
So can we also do transpose and then multiply it with another matrix which will invert its sign?
No.
Means,
No.
Means if you have a 3 cross 3 matrix,
Why will you take it? The 3 cross 3, they actually one way
yeah,
is you take the adjoint and all. That you take, but that is traditional way. I'll tell you, just using REF only you can find the inverse.
okay.
And it is very, very easy because you know REF. So you'll say, okay, REF is used in so many things. So that no, you'll appreciate REF. Like, why did you learn REF? Okay. Now, formula is this. A inverse is 1 divided by the determinant of the matrix A, which is AD minus BC. And then what you need to do, you have to swap these two entries, diagonal entries, and multiply the rest with minus 1. Now this works only for 2 cross 2 matrix, not 3 cross 3. Okay, now let me show you step by step for 2 cross 2. Again, first you calculate the determinant. Determinant will be 8 minus 3. So it is 5. So just apply the formula 1 divided by determinant of the matrix. So if the determinant is 0, so it will be 1 by 0. Right? So in that case, inverses will not exist. 1 by 0 is not defined now. So that's why you say if the determinant is 0, inverse will not exist. Anyways, now here you have to swap these two entries. So 4, 2, and then multiply these entries with minus 1. So this is your A inverse. So you multiply every entry by 1 by 5. 4 by 5 minus 3 by 5 minus 1 by 5, 2 by 5. Now if you want to verify when you multiply like this inverse is correct or not, you will say, okay, let's find out a product of A and A inverse. I think I have, yeah. A multiply with A inverse. So what will you get? 2 into 4 by 5. So in order to find this entry, so what you get? You take the dot product of first row of A with the first column of B. So what you get? 2 into 4 by 5 minus plus 3 into minus 1 by 5. So 8 minus 3 is 5. 5 by 5 is 1. Now you calculate this. So this is first row, second column. So you take first row of A, multiply with the second column of B. So 2 into minus 3 by 5 is minus 6 by 5. plus 3 into 2 by 5. So 6 by 5. So minus 6 by 5 plus 6 by 5 is 0. Similarly, you get 0 here. So this is 2 second row, first column. So take the second row of A, multiply with the first, take the dot product with the first column of B. So 1 into 4 by 5 minus 4 plus 4 into minus 1 by 5. So 4 by 5 minus 4 by 5 is 0. Similarly, you get 1 here. Okay, now I'll tell you shortcut method to find the inverse. So here, so this was A inverse. So by multiplying, you get identity matrix. So this means this is the correct inverse, right? Now let me tell you the shortcut method. Okay, so you start with this A augmented with the I. Okay, now you have to perform row elementary operations such that you transform A into I. So whatever row elementary operations you apply on A, same row elementary operations you will apply on I as well. Okay? Yes or no?
So we have to do A into this identity matrix, or?
No. So what I'm saying is, no. Don't get confused. I'll address your doubt. So A, by performing row elementary operations, you have to make it identity somehow by performing valid row elementary operations. Thus, whatever row elementary operations you apply here, same row elementary operations you will apply on identity also. So when A becomes I, after doing some row elementary operations, so whatever matrix you get it on the right, that will be your inverse. Okay, I'll take one example. For example, this, you have to find the inverse. This is 2, 3, 1, 4. So you have to make it identity somehow. Somehow you make it identity. So what you do? You say, okay, so for identity, I should have 1 here, right? You have copy with you, copy a pen.
Yes, ma'am.
Yes, ma'am. So what row elementary operation you will apply here so that you get 1 here? Because you have to make it identity. So you should introduce 1 here. How will you make it 1?
R1 minus R2.
2 of R2.
R2.
R1 minus 2
R1
of
minus
divide
R2.
by 2. Divide by 2.
ठीक है, R1 is R1 minus
R2.
2R1. So what will you
2
get?
R1. Right, 2
Oh,
R1.
sorry. So R1 is R1 minus R2. That's it, right?
Yeah.
This is what you are saying.
Yeah.
So okay, you will get 1 here.
So here you'll get minus 1.
1 here. 3 minus 4 is minus 1.
So it's not identity. Or again, we'll have to do.
Okay, let me connect my tab because I need to write. I have not shown all. Can I do it for 4 cross 4? वो easy हो जाएगा ना? Easy in the sense I have all the calculations done. Actually, my tab is not in working conditions. See, the thing is, row elementary operations you have to apply in the same way that we applied earlier. The row, so you are saying R1 is R1 minus R2. Don't do such type of rules because we have to go in the systematic way. So like you say, okay, R2 is, so first, this is the leading entry. Convert first this leading entry, this to 0. Okay, how will you convert this to 0? So you will say, okay, R2 is
R2 minus 1 by 2 R1.
R2 is R1, R2 minus R1 by 2. Okay. Is it okay?
Yes, R1 by 2.
Okay. So what will you get here? Here you will get 0. Okay, let me connect. Let me try for one time and then you will. Meanwhile, you do it in your copy. Can I show you for 4 cross 4?
Yeah, okay. Let's do for 4
Yes,
cross
ma'am.
4, I
Yes,
think.
yes.
Because if 4 cross 4 you understood, then you can do it for 2 cross 2. Okay? Slides is visible? Slide is
Yep.
visible? Okay. Okay,
But
let
these
me.
are not part of your main slide, or ma'am?
Yeah, no, it's not the part of main slide.
But can we get it somehow?
Yeah, sure. I'll post it in Teams. Teams I'll post. I cannot post it
Okay.
on the main page because other professor may not. They have different style now.
Okay.
Everybody has different style. So they'll use different, but the base slide is same. Base concept is same. We are covering, how to find determinant, properties of determinant and all. Okay, let's find out the inverse of this. Okay, first is find the augmented matrix. Augmented matrix is A and I, augmented with I. This is augmentation. Okay, now what you have to do is convert this matrix A to identity somehow by using some elementary row operations. Convert this into identity. So first step is before converting into identity, first you have to do REF. Same. REF you already know. So you have to convert these entries to 0. So again, you'll apply R2 is R2 minus 2 R1. R3 is R3 minus R1. R4 is R4 minus 3 R1. Okay. See, we have traditional methods, of calculating inverse that you have learned in 9th, 10th. But I can understand the computations are very complex, not complex. You need to remember the formulas. But once you know REF, so you know how to calculate REF. So REF calculation, if you know, you can solve many things. That's the stress point. Okay, make zeros below the first. So this leading entry is also called pivot. So this is the first pivot. Now our task is to convert these to 0. So you apply the elementary row operation. So R2 is R2 minus 2 R1. R3 is R3 minus R1. R4 is R4 minus 3 R1. Okay, you apply this. Now same row elementary operations you need to apply on this also. On this matrix. Okay, so R2 is R2 minus, so 0 minus 2. So minus 2 will get 1 minus 2 into 0 is 1 only. 0 minus 2 into 0 is 0. So whatever operations you apply here, same operations you have to apply here. Okay. Now consider the second row. Okay. Now R3 is R3 minus R1. So 1 minus 1 is 0. Minus 1 minus 0 is minus 1. Same row elementary operation you have to apply for row 3 here also. So 0 minus 1 is minus 1. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. All that. Then comes the fourth row. 3 minus, so this is R4 is R4 minus 3 R1. So 0 minus 4. Oh, sorry. So 0 minus 3. R4 is R4 minus 3 R1. So 0 minus 3 is minus 3. Then so you have applied same. Now the next target is you have to convert this into REF. It is not still in REF. So now next leading entry in row 2, the leading entry in row 2 you have to consider. So this is 1 and convert all these entries below this 1 to 0. How will you do this? Again, you use this formula. Now you have to make use of the row elementary operations involving row 2. So you'll say R3 is R3 plus R2. So right, so you'll get 0 here. 1 plus 0 is 1. 0 plus 0 is 1. 0 plus 0 is 0. Now same thing you have to apply for this also. Minus 1 minus 2 is minus 3. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. Okay. Now the thing is, now you go to, okay, for this also you need to convert to 0. So 2 minus this R4 is R4 minus 2 R2. So 2 minus 2 is 0. Okay. 1 minus 2 into 0 is 1. 1 minus 2 into 0 is 1. Now same thing you have to apply for this matrix. So minus 3 minus 2 into minus 2, minus 3 plus 4. So it is going to be 1. So 0 minus 3. What is this? Okay, sorry. R4 is R4 minus 2 R2. Minus 3 plus 4 is 1. So 0 minus 2 into 1 is minus 2. 0 minus 2 into 0 is 0. 1 minus 2 into 0 is 0. So you got this. Now come to row 3. Row 3 leading entry is this. Convert. Now the entry below this leading entry is 0. This entry should be 0. Okay, how will you do this? So now this, since we are looking at row 3 leading entry, so you have to do the row elementary operations involving row 3. So it will be R4 is R4 minus
R3.
correct. Now what is this
So,
matrix?
so we are doing the REF on the left and the original matrix, and we are doing the same elementary operation on the identity matrix.
Yes, correct.
And whatever. Okay. And what we are achieving
Now,
on the right hand side is the inverse, or
now the thing is,
or
you have got identity matrix. So I said you have to stop. The moment you get identity matrix on the left, you have to stop. And what you get now? Now this is the inverse. You can check also. This is the
Ma'am, I
inverse.
have just one question. Here, after our elementary operations, all the diagonal elements became 1, 1, 1, 1. But if it was like 2, 3, 4, 5, then what you would have done?
Suppose, okay, valid point. So suppose you say, okay,
no, we are only doing REF, right? We are not achieving identity matrix.
no, we have achieved our identity.
Yeah, but in this example,
yes, our motive was to achieve identity matrix only.
Now your point is valid. You say, okay, if the diagonal elements are, suppose this is turned out to be 4. Suppose. So this is not identity matrix. So in that case, you will say R2 is, how will you make it 1? So you'll say, okay, divide R2 by 4. This is again row elementary operation now. So you have to multiply this also then by, you have to multiply this also by 4. 1 by 4. Okay.
Now my next point is we were doing it as a shortcut, but I suppose the previous was more easy.
Previous was easy because it was 2 cross 2 now. If you do 3 crosses, then you have to calculate, adjoint and so on. See, that is just computation. You can have a look. But again, it will be too much.
You have to calculate the determinant, then 1 by determinant you have to do, then into adjoint matrix.
Yeah, adjoint again, that involves computation of minors, cofactors.
My point is shortcut is also not easy, man. That's one.
Shortcut is easy only for 2 cross 2. But if you scale it to say 5 cross 5 or 4 cross 2, it will take a lot of time. Okay.
So
Okay, these are
somehow
the.
you post these additional documents in our team, madam.
Yeah. And I request you can solve, practice questions. I have uploaded on web page, course page.
Okay. So that is for all 3 or all 4 classes or
all
the
sections, all
assignments.
sections. You have reference material also uploaded. I'll just show you since you have asked.
So the assignments we can do now, or we'll do only after all the classes are over?
No. This quiz 1 from lecture 0. I have
Zero
not
only.
covered lecture 0A fully. So you can solve quiz 1. It is ungraded, not to be graded. Solve it as per your own pace.
We do not need to upload this one, right?
Huh? No,
It's for
don't upload.
it's for our internal purpose, right? Yeah, right.
Internal means practice.
Practice, own practice, right?
Yeah.
Ma'am,
Okay,
but
now
to upload, is there an option to upload? Because we could not see anything like quiz section in the textbook.
no need to upload. Nah, no need. No, you don't upload answers. It is just for your practice.
Okay, got it.
And just one
Okay,
doubt.
now we come.
In your
What?
previous
Yeah.
slide where you had this 2 x 2 matrix, like I'm not able to find out its inverse using this REF method. It got complex. So later maybe if you can do it on a
No, it's
pen or
not
paper and
REF,
then
right? We are doing the row elementary operation to make the left-hand side an identity matrix. On the
So
right-hand
first,
side, we are doing the same operation.
yeah, and it
Just
got complex actually.
okay.
It get into fractions,
We
and
will do.
then I
fractions,
performed
it's
this
fine.
multiply and
It's fine. Complex is because it is involving determinant is 5 now. So that's why.
Hmm.
Oh, that 1
So
by
if you
5.
can, like after the class, if you can do it on pen and paper and upload that screenshot here in the chat, that will be helpful.
Yeah, sure. Thank you. Yeah, I'll upload. Don't worry.
Thank you.
Take second, just a second. Now, suppose now we go to elementary row operation. Oh, sorry. System of linear equations. Have you seen system of linear equations?
It's y is equal to mx plus c, right? Something
You can
similar to
see the
that, but
slide.
you'll have more
Yeah, that
You
is
can
features.
see
straight line.
You can see the slides.
Yeah.
Yes,
Okay.
madam.
Now suppose you are manager or you are
It
CEO.
is divided into two.
Huh? You are suppose CEO of some company and you want to maximize your profit. Okay. But at the same time, you should maximize your resources. Suppose you are CEO of some company which is making chocolates. Okay. Now suppose you are making milk dark chocolates. Dark chocolates are very expensive nowadays. So dark chocolates, so with nuts. Okay. So the thing is, so it will involve cocoa powder. And it will involve your nuts, dry fruit. Okay. And then you say, suppose okay, you have m equation. Okay. So right now, okay, I'll take only 2 minutes break. Okay. Only 2 minutes. Then I'll solve. Do I need to give motivation for the system of linear? Can I give it later? Because I want to solve questions.
It's okay, madam, if you want to.
Okay, ma'am. Okay.
Okay, I'll give you later. Maybe I'll upload a slide because otherwise we'll miss the concept. Whatever we have learned today, Arya, very important. I want to finish it off today. So this is a system of linear equations.
Ma'am, your presentation has changed, ma'am.
I think we connected from. You have to
Change me.
swap. You have to swap it, nothing else.
Is it okay?
Yeah, now okay.
Yes, sir.
So this is the system of linear equations. You have m equations, n unknowns. Okay. So x1, x2, xn, they are unknowns. You have to find these values. These are called linear because each variable x1, x2, xn, they're all having power as 1. Okay. And this is representing a straight line, each equation. Okay. Now what we do is AIJs, A11, A12, they're all the entries of a matrix. So this can be represented as AX is equal to B. I'll show you how. For example, if A is like this, Okay.
This
A
is
is
equal
A11.
to y is equal to mx plus c, right? That's a straight line equation or something.
Y is equal to mx plus c, right? But if x is 1, having like 5 n dimensions, so it will be m1 x1 plus m2 x2
Correct. Plus some
plus
intercept.
yeah, yes. So this all are representing the equations of a line, all these. Now, how this can be represented as ax is equal to b, that I'll tell you. So I'll say, okay. Oh God, this disappeared. Did it disappear?
No, ma'am, we can
Yes,
still
ma'am.
Yes, ma'am, I think.
It
Right.
vanished. Just a second, huh? Is it okay now?
Yeah. Okay.
Yes, ma'am.
So basically, this can be represented as ax is equal to b. Okay. Very loose. Anyways. Just a second, huh? Okay, I'll just take it out. Now, the thing is, this can be represented as ax is equal to b. Why? Can anybody try? See, what is your a? A is your a11 and
X is
a1n.
X is a coefficient or
Coefficients. Then last line is am1 and then amn. This is your matrix A. In between, you have the entities like A21 here, A21. Then you have here A2n. Okay, so and what is your x? X is a column vector. This is the vector of unknowns, column vector x1, x2, and so on till xn. Okay, this is equal to b1,
B1.
b2, bn. They're m rows. Okay. Now, if you multiply this row with this column, what will you get? A11 into x1. Just a second. You get a11 into x1 plus a12 into x2 plus a1n into xn is equal to b1. So this is the first equation. Okay. Second equation, similarly, you do a21 into x1 plus a22 into x2 and so on plus a2n into xn, which is equal to b2. Okay. So now what is this matrix? This is a matrix of coefficients. A into x is equal to b. Okay. Got it? Now, you
What
have
is
to
matrix of coefficients?
this is the matrix of coefficients. A11, A. So this is you're multiplying coefficients with this unknowns. A11 is the coefficient in the first column. So you have to multiply with x1. You just do the matrix multiplication. That's it. A11 into x1 plus A12 into x2 plus so on A1n into xn. Then go to the next row. Next row will be A21 into x1 plus A22 into x2 plus so on A2n into xn. Now you go to the last row. Last row will be AM1 into x1, AM2 into x2 plus so on AMN into xn is equal to BM. Now whatever you have learned, so this is AX is equal to B. Now right now we are focusing on how to find the solution of this linear equation. So you represent this as you just augment the A with B column. Just take the coefficient matrix A, augment it with the B column. Okay, this is called the augmentation. Now, what you have to do, you have to solve for these x1, x2, xn. You have to find, because these are unknowns to you. You need to capture, you need to find what are the values of x1, x2, xn. That's how you'll solve the system of linear equations. There are many equations. Now consider this system of linear equations. Now here we have to find what is the x1, what is the value of x1, x2, x3, such that all these equations are satisfied. Okay, right? So we again construct the augmented matrix A augmented with B. You construct
What
this.
do you mean by augmented by B, ma'am?
So like we have seen it earlier also, no? Augmentation means add, concatenate, not add, concatenate. Like we added here. Sorry. Like we added here, now. This is augmenting. Okay. Okay. Now what I'm trying to say is, you have to find for what values of x1, x2, x3, this equation is, all these equations are getting satisfied. Okay. So what do you do? So here the first, it says, okay, it says add the first and second equations. So on adding first and second equations, you get 2x1, you add 2x1, here this will get cancelled, plus 3x3 is equal to 5. But the thing is, 2x1 plus 3x3 is 1. So you substitute 1. You will say, okay, 1 equals to 5, but this is not valid, right? This is inconsistent. Right or not? You agree or not? This is inconsistent now.
Yes.
Yes.
So this is inconsistent. Now you just modify this example. Modify this example means this is your new problem now. You have modified something. Now what you do, you say, okay, if you add, okay, it says that, okay, if you use first equation and the third equation,
You can find it.
first and third equation, you just subtract this equation, third equation, you just subtract the third equation. Okay. Okay, just a second. Huh? You try it in your notebook. Subtract the third equation from first equation. What will you get? Tell me.
x1 equal to 1.
X1 is equal to 1. Now what you do, you have got the value of x1. Now you substitute the value of x1 in first, or you can say in second and third equation. I'll just now I think it's working.
And these are like simultaneous equations which we did. But that was only for x and y. Here it is x1, x2, x3.
Yes. What will you do now? Now here, substitute x is equal to 1 here. So what will you get? Minus x2
plus 2x3 1.
Is equal to 1.
1.
Plus 2x3 is equal to 2. Okay. and then
One.
make use of this
Equal
third
to 1,
equation.
na?
One.
Ma'am, 1.
1,
X1 is
1.
1 now.
Sorry. Okay, sorry, actually. It's 1. 1. Now refer to this.
X2
Use
plus
this
X3 is
equation
equal to
also.
2.
2x3
Is equal to
You write
3.
x2.
X3 is equal to 1.
X2. This is minus x2 plus 2x3 is equal to 1. Now add this equation with this third equation. What will you get? You get this gets cancelled with this minus x2, right?
3x3 equal to
So 3x3 will be
3x3
equal
3x is
to
equal to 3.
3
x1 equal to
3x3 is
1.
equal to 3, right? So 3x3 is equal to 3.
X3
That means
1.
x3 is going to be
1.
1.
1. So you have got a unique solution. So every variable is having just one value, like only one value, which is 1. So this is a unique solution. In the earlier problem, you got, okay, you are getting inconsistent solution, right? And here you're getting unique solution because there is only one value of x1, only one value of x2, and one set of values for x1, x2, x3. So you say this is having unique solution. Now again I modify. Now I say that, okay, now if you add the first and second equation, just add first and second equation. So x1 plus x1 is 2x1.
2x1
This gets cancelled with
plus
this.
3x3.
3x3 plus 3x3 is equal to
5.
2 plus 3 is 5. You get this. But this is this equation. So you say, okay, this is kind of redundant information available to you, right? Isn't it?
Yes.
So
Yes, ma'am.
now you say, so this 2x1 plus 3x3 is equal to 5. So this is same as the third equation, which is this. Now, solution to these three equations, it should satisfy this 2x1 plus 3x3 is equal to 5. Now there are infinite many solutions. Why? Because there are infinite values of x1 and x3 that will satisfy this. Say you can say, okay, x1 is 1, x3 is 1 solution. Next could be, there are many such values. So
Yeah,
for
I
example,
know some
you say
person.
2x1 is 5 minus 3x3. You bring 3x3 here, minus 3. Okay. So what do you get? So x1 is in terms of x3. Now you substitute x1 as this in first equation. So x1 is in terms of x3. So you get this equation in terms of x2 and x3. So you'll get this. So now both x1 and x2 are in terms of x3, right? So x3 is kind of a free variable. It is a free variable. So why this is having infinite solution? The moment you change x3, if x3 is 1, so x1 will be 5 minus 3 by 2. It is 1. And if x3 is 1, so 1 half plus half is again 1. Now if you change x3 to 2, you will again get some difference. So that's why you are saying there are infinitely many solutions here. Why you are getting infinitely many solutions? Because this equation is redundant. There is a redundancy here. Okay, that's why you have infinite solutions. But now let's make use of the REF forms. Okay, how? See, these were just three equations. You add, subtract, you say, okay, let's pick these equations. Now, can we have some systematic way to find out whether the solution is unique, infinite, or it does not, like inconsistent? So let's figure out that now. Okay. So here x3 is like free variable. You can say it's a free variable. And x1 and x2, they are the pivot variables. They are corresponding to the leading columns, pivot columns that have leading entries. I'll just wait for a while. I'll tell you all this. So we'll go first. We'll solve using the systematic way. How do you find out whether the system of equations is having unique solution, whether it is having infinitely many solutions, or it is inconsistent. Let's do one by one. Like let's solve that. Okay, is it okay till now?
Yes.
Yes, ma'am.
Yes, ma'am.
Time is okay. I'll stop after this. Okay, just this equation. So again, this is system of equations. Now you have to find for which value of a this is giving you unique solution, for which value of a it is giving you infinite many solution, and for which value of a it is giving you inconsistent. Let's figure out. Okay, so again you have augmented matrix. Now whatever knowledge you have used, whatever knowledge you
Hello.
I think we lost
I think we lost,
the
ma'am.
connection.
Yeah. Is it 2 hours? Then it will.
No, she lost her laptop battery.
Oh.
It was almost down while
I
she
think
was
our
sharing.
time is also over.
Next class is on Tuesday, right?
Yes.
Yeah, Tuesday and Thursday. Yeah.
Oh, these are weekend classes, right? Why they are keeping in the weekdays actually? The office
Only for
time.
these 4 classes.
So
After
these are
that,
the this basic classes. I think that's why they schedule. But actual
No,
classes will
Tuesday and
teach.
Wednesday. Tuesday and
When we'll
Wednesday.
get the, anyone know when we get the detail about our regular subjects
Yeah.
or AI and
We
ML?
can say the next
Next
week
weekend.
onwards we'll learn the next only weekends, right?
Correct.
It's not
Correct.
updated on the calendar. I did check.
Yeah, it's not updated. Correct.
Yeah.
But maybe weekend na next Saturday, Sunday, maybe Saturday before the Saturday will be get all the information, and our
yeah.
classes mostly will be on weekend only. That will be actual
Yeah,
our.
you'll have classes in weekends. Yes, yes. Correct.
Ma'am joined.
Okay.
Yeah, sorry, it was power. Okay,
No
I'll
issue, ma'am.
just share.
You
no
can
issue, ma'am.
Will
Madam, can we
we?
continue in the next class?
Next
Yeah,
class
ma'am.
we can continue. It's already 10:30, madam.
Yeah, ma'am.
Okay, fine. Okay, no problem.
Can you
You will have
upload this
Ma'am,
PPT?
ma'am, one quick query, ma'am.
I'll upload.
So in the coming time, all the classes will be like late night or over the weekend,
No,
or
no,
there will
no.
be some morning classes as well.
Morning. Actually, this is because other faculty are busy in the morning. But now from now onwards, you'll only have class. See, 0 classes are only scheduled in nights. Rest all classes
Okay.
are on time. Okay, I'll upload the slide.
Ma'am, what
What
will be the timing of the classes, ma'am?
So your classes 0 session will end on Wednesday. Tuesday, Wednesday will end early, 7:30.
Okay. But from next weekend,
Yeah.
what normally what will be the schedule in the morning hours only?
Morning till evening, like 2 classes you have in the morning, like 9 to 11, or maybe 8:30 to 10:30, then 10:30 to 12:30, then 2 to 4, or 1:30 to 3:30, then 4 to 6. Okay, I'll just stop.
There will be
Throughout the
4
day we have
classes.
classes, or is it only half day?
See, if your classes in between 2 classes you'll have on Saturday, 2 class on Sunday.
Okay.
But
Ma'am,
Okay.
If should I continue?
maybe tomorrow we can.
Acha, ठीक है.
But
Okay,
for
I'll just...
Max Foundation, you will be coming, madam, or someone else will
No,
conduct?
I'll not be. I cannot come